All right, welcome everyone. Thank you for joining this talk about open and interoperable AI using ONNX. My name is Prasanth. I work on the Microsoft AI platform. And so before we dive into a bunch of the material, I wanted to kind of give a little primer about machine learning. I was talking to several of you in the audience, and some people are doing machine learning, some people are learning about machine learning, some people work with people who do machine learning, et cetera. So I just want to make sure we're all kind of level set on the vocabulary and kind of the process. So here's a primer. So we all kind of know about programming. You write an algorithm in code, you give some input, and you run it on the computer, and you get an answer out. So that's programming. So with machine learning, it's kind of flipped around. You give it some input, you give it the expected answers, you run it on the computer, and you get an algorithm out. So this is great for problems where it's kind of hard to write an algorithm and you have to have the machine kind of figure it out from the data. So we have some different terminology, though. That input data to machine learning, we call it training data. The thing that works on that training data to produce the algorithm is called the training framework. The thing that it produces is not an algorithm. We call it a model, which is an algorithm inside of it. And then we operationalize that model and put it back in so that we can run different inputs through that model and get answers. And we don't call that programming, we call it inferencing. And the thing that does inferencing is called a runtime. Okay, so that's the 1-minute machine learning primer. Now you know everything about machine learning. And then, of course, you take that back into as a feedback loop and improve your training data. So why is open and interoperable AI important or interesting? Well, if you're doing all your training using one training framework and then deploying it to one platform, which uses one specific type of hardware, it's fairly straightforward. You can optimize that to make sure that it performs really well when you do that inferencing. Because when you do inferencing, the performance really matters. But if you are like most customers and most organizations, including Microsoft, you're using models from a variety of training frameworks. You're not just using one. And these different training frameworks have different formats, different things going on. And then if you want to optimize the outputs of those training frameworks on different hardware or on a single hardware to begin with, you have to do some work. You have to make sure that you can process all those different formats and make it run really fast on that particular hardware. But then the situation becomes even more complex. Oftentimes, you're not just deploying to one platform and one hardware. You're deploying to a bunch of different things. You're deploying to mobile, you're deploying to cloud, you're deploying to the PC, you're using all sorts of chips to accelerate the inferencing. And now you have like this huge matrix. You're trying to optimize like all possible formats against like all possible platform and hardware combinations, and it becomes difficult. It's not really scalable. So this is where having something that helps with that process comes in really handy. And that something is ONNX. So what is ONNX? Well, it stands for Open Neural Network Exchange. It's basically an open format for machine learning models. It's all open source, so you can actually check it out on GitHub if you're interested. So with this format, it's actually developed by a community of companies who kind of share this vision of open and interoperable AI, basically allowing people to use different frameworks, right, to create their models and deploy them in multiple places. So we have a great set of partners who are working together on developing this format as kind of a standard. So going back to this diagram, once you have ONNX in the picture, it makes it a lot easier for data scientists and developers to have the freedom to choose the framework they feel is best for them. It could be the right thing for the job they're doing. It could be familiarity or experience with the framework. Whatever the criteria is, they can choose the framework they would like to. They also can have the confidence that whatever they produce can run on a variety of target platforms and hardware. So they're not always locked into a specific deployment target. And that's the value of open and interoperable AI and of ONNX. All right, so on the agenda, I had 3 things. We've already done 1. So for the rest of it, we're going to talk about the other 2. How do you actually create ONNX models, and how do you actually operationalize them? So This kind of takes that previous diagram, which is a little abstract, and turns it a little more concrete. So you can basically create models using a couple of different things that we're going to talk about. Once you get the ONNX model, you can deploy it to the cloud and to the edge, and you can actually run the same model on both, in all of these places where you can deploy it. So we're going to talk about all of these components in some depth. All right, so the step 1 is to create, and step 2 is to deploy. So let's talk about step 1. So how do you actually get an ONNX model? Well, there's 4 main ways of obtaining an ONNX model. First, we're going to go through each of these. So the first one is something called the ONNX Model Zoo. So this is a collection of pre-trained ONNX models. So people have basically created these models, and they've kind of curated them, and they've published them here. So if you go to that website, you'll see like a list of different models and in different categories, and you can kind of click through and download the version that you want, and then there's information about like how you would actually integrate it, et cetera. And we're going to do a demo kind of walking through this and seeing how that works. The second way you can get models is through Azure Custom Vision Service. So if you go to that URL, you get this nice little service where you upload your photos and you label them. Right? So you'll say, I don't know, flowers or of a certain type or flowers of a different type, et cetera. You click on a train button, and then it produces an ONNX model for you. It's kind of like magic, but it's actually doing a bunch of work in the cloud to take your data, using the information from that data to personalize and customize an image classification model. And then it makes that available for you to download as an ONNX file. The third thing that we listed was around converting models. So let's say you already have a bunch of models. Either the data scientists in your company have created some models, you found some models on the internet, like someone published some cool models. You have models from somewhere, and you want to make them run with ONNX. So what do? Well, you can convert them. So all these frameworks either support ONNX or have conversion support for them. So the general process is 3 steps. You load the existing model in the format that it's already in. You convert to ONNX, and then you save the file. And I put convert to ONNX in parentheses because sometimes step 3 takes care of step 2 for you, as we'll see in one of the examples here. So Keras is a popular training framework, and this is example code for how you would actually convert a Keras model into ONNX. So you include the Keras package, you include this converter package called WinML tools, you load the Keras model, you convert the Keras model, and you save it into ONNX. So just like the 3 steps that I described, that's what it looks like in code. So Chainer is another popular framework in some countries. And again, same thing. You import the packages. It's all Python code, so you do this import syntax. You load the model with the Chainer. You actually have to specify some sample input, so it knows how to create the ONNX file, and then you export that into an ONNX file. So again, just 2 or 3 steps, depending on how you're counting, to get an ONNX model. PyTorch, again, same scenario, similar scenario, where you load the model, set some input data, export it, and you get yourself an ONNX model. And we'll do a demo of this one later on with an actual model using Azure Machine Learning. And then there's TensorFlow, same thing. The syntax is a little different, but basically you're passing in the input model, you're specifying the output model, and it's doing a conversion when you run this program. And then the fourth way of getting ONNX models is to actually train your own model in Azure Machine Learning. So you've probably heard about Azure Machine Learning in some of the keynotes and some of the other talks that you might have gone to during Ignite. And basically, Azure Machine Learning allows you to experiment locally, but then actually scale up to use all the GPU power in the cloud. And it helps you speed up data science with some automated machine learning and hyperparameter tuning. There are a lot of features that help you kind of create the most optimal model for your scenario. And then it also provides ability to kind of track your experiments, manage the different runs, because you're generally iterating a lot and doing a lot of combinations and kind of figuring out which one's best. So you need to track all that data to kind of figure out which model do you want to actually export or to save into the ONNX format. So this is the fourth way of generating an ONNX model. You actually train it, and then you save it as an ONNX file. And we'll do a demo for this. So that was a quick run through of step 1. So let's talk about step 2. So you have this ONNX model, and now you want to deploy it. So how do you do that? So like I said earlier, you can deploy to the cloud, or you can deploy to the edge. And it's basically the same model that can be deployed in multiple places. So that makes it really nice. You don't have to worry too much about, OK, I have to save this version of the model for this and save this version of the model for that, et cetera. So if you're deploying to Windows, there's something called Windows ML that's actually built into the operating system. Now, this is really cool because it's actually available across the entire Windows family of devices. So whether you're running on like an IoT thing or you're running on Windows Server 2019, it's there. And it provides a hardware abstraction using DirectML. So many of you are familiar with DirectX. It builds on top of that to provide machine learning capabilities using the GPU acceleration underneath. And so you don't have to worry about which type of hardware you have in there. Like, as long as the hardware card that you have in there works with Windows, it'll work with your app. You don't have to worry about like which manufacturer it is, or you don't have to do that kind of specific stuff in your application. There's also the same API whether you're building a Win32 app or a modern WinRT app. And it's optimized for performance, and it's virtualization ready. So if you're running it in a VM, you'll still get access to the Windows ML. So you can also deploy to the cloud using Azure Machine Learning. This basically provides model management services so that you can deploy as a web service to ACI, Azure Container Instances, or AKS, the Kubernetes service. And it also allows you to capture model telemetry, so you can kind of create that feedback loop and see how your model is doing. All right. So the first demo I'm going to show is taking a model from the model zoo and deploying it as a Azure web service. So this is the model zoo that I mentioned, right? GitHub ONNX models. And you have a bunch of different types of model scenarios, image classification. We're going to use ResNet. And then you can download the actual model here. And so I have this Jupyter notebook, which is a kind of a way to express tutorials. So the steps are basically you download that file from the model zoo, expand it on your machine. And then you start using the Azure ML SDK to deploy it. So you first create a Azure ML workspace. You register your model into that workspace with Azure ML. So this is the model path that we downloaded. And you can see all the other models that you have registered in that workspace if you want. And then this is kind of the heart of the thing that we're doing here, which is around scoring. This is the scoring file, which actually does the inferencing. And there's two kind of required components, or two required methods in the scoring file. There's an init method that's needed, and there's a run method. The init is called when the service starts up. So you want to do all your initialization in there. So we are using the ONNX runtime, which we'll talk about more in a little bit, to run this ONNX model. So we basically specify the model name, model path for that, and start a new inferencing session. That's the initialization. And then when we're ready to run, so this run method will get called every time you invoke the web service. So it gets this input from the query string as a JSON, right, in the body of the request, basically. And I like to usually, so you can basically write your run method any way you want. It basically takes in, the input is JSON, you have to return JSON basically. I like to structure it to have some pre-processing step, an inferencing step, and a kind of post-processing step. So for pre-processing, I basically take the input data, turn it into an array using NumPy, which is a Python library, and then I do this normalization. So how did I know how to do this normalization? Well, with the model zoo, the models actually have some documentation that describe what kind of input the models expect and what kind of pre-processing you need to do. So there's some code here. I just literally copied and pasted that into my scoring file. So it basically takes the image data and it has to normalize, like the pixel data has to be between 0 and 1 for this particular model, and it needs to have a certain data type, and it needs to be, have a certain mean and standard deviation applied to it. So that's what it's doing. And then we call the ONNX runtime, right? We created that session earlier, the ONNX runtime session here, right, by loading up the model during the initialization. So we basically call that. We do a run method on it, on that session. We pass in the input data that we pre-processed, and we get some output data. And then with the output data, we do a little bit of post-processing, and then we return it. The post-processing in this case is applying a softmax on it. So basically, the model is returning an array of probabilities, and softmax is a mathematical function to basically turn that into values between like 0 and 1, basically. So you just apply that on those results, and then you return it. So that's the scoring file, right? And this is going to be part of the container that we deploy. So we create a container image. We specify that we want ONNX runtime installed in there. And then you basically have Azure-ML create that container for you. I'm not running it in real time because it does take a few minutes. So I ran this earlier today, and so you'll see the output. When you actually run it yourself, you'll see output like this, and it'll take a few minutes to run. Once you have the container image created, you deploy it. Here I'm deploying it as an ACI web service. For production scenarios, you would deploy it to AKS. Similar process, though. Once you have the web service deployed, again, that takes a few minutes to deploy. So I've already run it previously. Once you've deployed that, you can actually get the URL for it. So I went through all of these steps, and I ended up with a REST endpoint that's hosted at this URL. So this is a REST endpoint. It just takes JSON as input and returns JSON. So we wrote a little app that actually calls that. So I'm going to paste that URL that I copied right from here. And ResNet is an image classifier, so you specify some images. So these are images that I took on vacation, and it'll tell me what it is. Okay, it's a daisy, it's a monarch butterfly, and it gives probabilities for the different classes that it's identifying. Let's see what it says for this one. Okay, it's a coral reef. And ResNet has about 1,000 different classes that it can identify. So that's the ResNet model, and you've seen how we take a ONNX model from the model zoo and deploy it to an Azure-ML web service. Now, I want to talk a little bit about the ONNX runtime that I mentioned, when we did that demo. So ONNX runtime is a high-performance runtime for ONNX models. It supports the full ONNX ML spec, so it supports the DNN and traditional machine learning parts of the ONNX spec. And it has an extensible architecture, so you can plug in different hardware accelerators. And it also has a very simple Python API, as you saw in the demo. So let's talk about the Python API a little bit. So basically, it's pretty simple. You import the ONNX runtime. It's a Python package. And then you instantiate an inference session, specify the model path or model file name, and then you run the session. You run the model in the session by specifying the input, and you'll get back the results. So what are ONNX models? Like, we've been talking a lot about creating ONNX models and deploying ONNX models, but what is an actual ONNX model? Well, an ONNX model is a graph of different operations. Operations are basically the mathematical functions that you kind of are the building blocks of creating the machine learning algorithm. So when you actually visualize an ONNX model, it looks something like this. It's a directed graph, acyclic directed graph with the different operators. And there's a neat tool called Netron, which allows you to load any ONNX model and view it. You can basically kind of see all the different operations that are going on in that model, and you can get view the metadata of the model, et cetera. This is an open source tool that's available from linked from the ONNX website. So this is the input, right? This is the model that's going into that ONNX runtime. So what does the ONNX runtime do with it? Well, here's let's geek out a little bit, and here's the architecture slide for what it's doing in there. So you have the input data coming in, and you have the ONNX model coming in, right? So when we load up the ONNX model, it loads it up into memory, and it partitions the graph. It basically is trying to find how to run each of those operations in the most efficient way possible. And this is where those execution providers that I mentioned come in. So some operators are going to be fast on certain types of hardware, and others will be faster on other types of hardware. So we want to kind of make the best use of the hardware that's available and run your model as efficiently as possible, right? So we have these different execution providers that are basically plugins. They register themselves with the ONNX runtime, and they say, OK, I'm this provider, and I know how to handle this set of operations really fast. I've optimized for those set of operations. And then the graph engine inside of the ONNX runtime, basically, when it's parsing the graph, it figures out, OK, these set of operations need to go here, these need to go over there, and then I'm going to combine the results, et cetera. And that's how we get the high performance. And then, of course, at the end, you get the output. So we work with a number of hardware companies to create these execution providers. And one of the companies we work with is Intel. So I'd like to invite Padma up here to talk a little bit about the work we're doing together for ONNX runtime and the Intel chips.
Thank you. Thank you again. And so I just want to talk about what we are doing with Microsoft in collaboration with Microsoft, especially on the ONNX runtime. OK. I do see it. OK, thank you. So basically, Intel, first thing is I do want to say that we are very, very supportive of the open AI system, open source AI ecosystem. And we are actually a proponent of this whole collaborative work with all of the companies. And especially with ONNX, we are partnering with Microsoft and other companies to develop the specs for ONNX. Okay. And in terms of ONNX, because of the interoperability and interchangeability between the different AI frameworks, it makes it easy for us to focus our efforts on optimizing the silicon for this one particular open software stack. Intel has also spent a lot of time optimizing the hardware and the silicon for the different frameworks. Like we have people working on TensorRT, we have people working with MXNet, CNTK, Caffe, et cetera. And now, in addition to that, we have started working with Microsoft on doing the optimizations for the ONNX runtime. As part of this, we have actually started, as you might know, we already have Xeon processors which support the math kernel library. We have a special math kernel library, especially for neural networks. This neural networks, basically this math kernel library optimizes for performance. It provides vectorized instructions, and it provides building blocks for somebody to implement convolutional neural networks with C and C++ APIs. So let's go to the next one here. So in terms of this, you saw this architecture of the ONNX runtime. What we have here, we have done is we have integrated two different execution providers inside of the ONNX runtime. One of them is ngraph. The other one is MKLDNN. I just mentioned about MKLDNN, which has the mathematical libraries for use. And ngraph is a graph compiler. It is built on top of MKLDNN, and it provides for scalability and for scaling across heterogeneous hardware accelerators. So with the orchestration between ONNX and the ONNX runtime and the ngraph, we can provide seamless integration and transparency for the end users between the software and the hardware. So in terms of NGraph, we do not, the developers do not, or the framework users do not need to understand the low-level details of the hardware, and they don't need to worry about programming because we provide that backend support. NGraph is open source, and it abstracts away so that the developers don't have to worry about the details. Some of the optimizations that we have done in terms for NGraph especially are fusing of operators, because the NGraph will know which are the backends and what are the capabilities. So it will optimize the backends for the best performance. We do data layout changes so that we can help with memory footprint sizes, data storage, and memory bandwidth concerns. We also have some compilation techniques. We do DEX compilation, and we are planning to add ahead of time compilation so that we can integrate and run the graphs which we are getting back from ONNX, from the ONNX runtime, to run them faster on the accelerators. Today we have Intel Silicon in the cloud, and so when you deploy your workloads in the cloud, you can be rest assured that you will get your workloads will be best accelerated on all of the Intel processors. Soon we will be adding, in the next couple of quarters, Intel is releasing the DL Boost technology, which is basically vectorized neural network instructions, which are specifically tailored for speeding up and enhancing the performance of neural networks. And that's about all I had for now. Anything else, Prashant?
Cool. Thank you so much. So thank you for the presentation, also for your ongoing partnership. We like working with the different hardware companies because they understand their hardware the best. They can make sure that they are optimizing the different operations, the operators that we talked about. How to optimize that on the different hardware, they're the experts at. So we want to make sure that we plug in the best technology that they have to offer and make it available to you through the ONNX runtime, so that you get the full ONNX compatible runtime, but still making use of all the different accelerators that different hardware companies are providing. So I'm going to show another demo. This time we're going to do ONNX conversion. Right? Last time we just downloaded it from the model zoo. And this time, we're going to show how you would convert a model that you found somewhere that is not in the ONNX format. So YOLO is a you only look once. That's the name of the model. It basically does object detection. Multiple objects in the picture can be detected at the same time. And in this example, we're going to take a Core ML version of this model. There's a website that has a bunch of Core ML models. This is one of the models that's listed there. It's not in the ONNX format, though, but that's OK, because you can download it. Right? You download it locally, and you run a conversion script, very similar to that Keras one that we looked at earlier. Right? You load the model, you convert it, and then you save it. And then you kind of go through the similar steps as what we did earlier for the other model, where you instantiate a Azure ML workspace. You register your ONNX model with that workspace. You write the scoring file. In this case, the pre-processing and the post-processing is fairly simple. You just turn the JSON into an array that the model expects. And then you create the container image. You deploy that container. And then you deploy the web service based on that. And again, I've run these ahead of time because it does take several minutes to do all those deployments. So once that's up and running, you get, again, an IP address or a URL of where that service is hosted. And we can call it. Let's see. All right, we're calling it from this little app. We're going to take a picture. We're going to, let's see. So it should be able to recognize two things in this picture. Let's see. OK, there we go. The lighting is a bit weird, so at least it recognized me. It has 30% confidence that I'm a person. That's pretty good. it didn't see the bottle. There's some shadows going on, so let's try that one more time, and maybe it will work. Okay, well, I think the lighting is a bit weird. So, I took a picture of myself holding a water bottle in the hotel room. So let's see. Okay, so this one, it recognized there's a person and there's a bottle as well. So anyway, so it's calling this model that we just deployed, right? This model was not originally in the ONNX format. We converted it from CoreML into this format. And you can do that pretty much with all those other formats that we talked about earlier. All right, so depending on the workload, sometimes you'll want to use CPU, sometimes you'll want to use GPU. Azure has both for your use, right? We have great CPU support, and we also have great GPU support. So we also work with NVIDIA on making sure that when you run your models on GPU, you get the best performance possible. So I want to invite Mohammed from NVIDIA to come talk a little bit about ONNX and the integration work they're doing.
Thank you. Thanks, Prasant. First, I want to thank Prasant and the Microsoft team for the collaboration and the opportunity to talk here. Let's see, do I have the right slide? Okay. So as Prasant indicated, NVIDIA is working with Microsoft and other partners in the ONNX ecosystem to enable more use and more simplified development for AI applications. And one of the mechanisms we use, one of the key platform software that we use that we're working with Microsoft on is our TensorRT platform. It is our runtime engine. It has two main functionality. One is optimize the models. Obviously, some of the models may not be optimized when you first develop them. So the TensorRT optimizes the model by doing layer fusion and other functions, as well as determines what is the right libraries to use for the different GPUs that you may deploy on. As Prasant also indicated, we have a number of GPU instances available in Azure, from lower end to higher end level performance capabilities. So depending on your use case and scenario, the TensorRT will select the appropriate libraries, as well as if you have edge devices as well. So first thing TensorRT does is the optimization. And it also allows you to even go in lower precision from FP32 down to int8 or FP16 while maintaining the same accuracy or very close accuracy to your target. So there's a lot of functionality that's available there. TensorRT also allows you to deploy on the GPU. So once the file is optimized, then you can run your application, call TensorRT, and then run your application using for that inference scenario, run the model. So we've obviously collaborated with Microsoft to enable both using of CUDA, our programming libraries and so forth, as well as using TensorRT, so that way when you use the ONNX runtime service, you get absolutely the highest performance capability on using Azure-ML. So I'm just referring back to the block diagram that in terms of how it runs within the ONNX runtime. Today, we have with CUDA support, and we're working closely with Microsoft on support of TensorRT to ensure you get the maximum performance when you deploy using ONNX runtime. And that's
great. Thanks so much.
Thank you very much.
Again, thanks for the presentation. Also, thank you for the ongoing partnership. So again, this kind of, it's the same point we said earlier where, if you use ONNX runtime, we want to make sure that you get the best performance possible on whatever hardware you're deploying your models to. So let's do another demo. And this is a scenario where you actually train in Azure ML, and then you actually deploy to Azure ML as a web service as well. So let's pull this up. So MNIST is a data set of handwritten digits that are used to train models to recognize handwritten digits and figure out what number they are. It's a very popular model. It's kind of a simple model, but we wanted to use it to kind of show all the other parts. If you went to the Windows ML talk this morning, they showed an application using the MNIST model, the ONNX model, that was generated basically by running this. So with Azure ML, again, to do your training, you also create a workspace, right? That's kind of your object that holds everything inside of it. And then you create a remote computation target. So in this case, we're actually using a GPU cluster, but you can use a variety of different computation targets. You basically create the project directory, and you upload a training script into there. Now, this training script looks something like this, right? This is a PyTorch training script. It basically defines kind of the network topology that you want to do, and then it iterates through a bunch of the input training data to kind of refine the weights of that topology, and then test the accuracy of how that training is going. And in order for us to save this output as an ONNX file, we just had to add a few lines at the end of that training script. So this training script I actually got from like a PyTorch tutorial. MNIST is one of those models that you use. It's like a hello world, right? So I got that training script, and then I modified it to add these 3 lines at the end where we specify a sample input, the path, and then you save it as an ONNX file. So now I've uploaded this training script into the Azure ML service. You create an experiment, and then you create a PyTorch estimator. So PyTorch has a estimator kind of built into the Azure ML SDK. And in this case, I also want to upgrade the version of PyTorch that I'm using to 1.0 because it has a little bit better support for ONNX. PyTorch 1.0 preview was released a few days ago, so I'm using that. And then I submit my job. Basically takes all the training script and the data and everything and runs it in that cluster that we created. And then sometimes the jobs take a while depending on how much data you have and how big the model is, so you can actually monitor your run. Again, I've run this earlier in the day because otherwise it would take too long to do during the demo. And then when it's done, okay, it says run is completed. So it basically has produced this list of files, and one of them is mnist.onnx. So that's the actual model. So I can download it if I want, right? I can actually download any of these files, including that model, and have it locally if I want. But in this case, we're just going to go from training to deployment. So I can just register that model, right? I can just register it with that with the workspace. Again, I can see all the other models that have been registered in my workspace. And then I write that scoring file, just like we did in the previous examples. In this case, again, the pre-processing and the post-processing are fairly simple. I just convert the JSON into the array, the tensor input that the model is expecting, and then I run the session with the input data, and then I get the results. And the post-processing here, I do argmax, which is basically it picks. So the output of the model is an array of the different number, like 0 through 9, with the confidence level of which digit the image corresponds to. And argmax just says pick the highest one, the one with the highest confidence. So that's the scoring file. I include that in the container that I'm building. I also include the ONNX runtime. And then I deploy that image, or create the image, and then I deploy that container. Again, I'm using ACI here. You can also deploy to AKS. It takes a few minutes to deploy, and once it's deployed, you have a web endpoint. You probably know what I'm going to do. I'm going to paste it here, and we'll see if I draw some numbers. Will it recognize it? Great. Let's see if I can, what it'll do when I do this. Okay, it didn't get that one. There we go. So again, this is an example where we've taken it from a training script all the way through deployment using Azure ML with ONNX as the format, bridging that. All right, so let's do a quick recap. So we had 3 objectives originally, and I think we've hit them all. So what is ONNX? It's basically an open standard, so you can choose the right tools for the job you're trying to do. We don't want to mandate or constrain you to a specific framework. You should be able to use whatever it feels right for you. But you still want to have the confidence that the models you produce will run with high efficiency and high performance on whatever platform you're targeting for deployment. And how do you create ONNX models? We showed 4 different ways of creating ONNX models. Some of them are just downloading models that exist. Some of them are converting things, or you can create your own from scratch as well. And then operationalizing ONNX models, if you're deploying to Windows, there's Windows ML. There was a talk earlier today that showed how in detail like how you would deploy a model into a Windows application. And then, of course, if you're deploying to the cloud, you can use Azure ML and the ONNX runtime to do that. And the ONNX runtime makes sure that you get the highest performance independent of the hardware that you're deploying to, because we partner with different hardware companies and make sure that their best acceleration technology is available to any user of ONNX runtime. So how can you try this out for yourself? Well, we've released the preview version of the ONNX runtime. It's already available. It's live on PyPy. So you can actually do a pip install on ONNX runtime, and there's a GPU version of it as well. And it's supported for Ubuntu and Python 3.5 and above. So you can actually try it out for yourself. And there's more documentation and samples at that URL. So there are a few other sessions that might be of interest to you to call out. Some of these might have already happened, so you can watch the recorded version of it, and some of them are still coming up. The Windows AI one, the one at the top, was the Windows ML one. That's already happened, so you can watch the recorded session. Tomorrow we have a machine learning with ML.NET one. That shows you how to create a model using C# APIs and then export. You can use ML.NET to export an ONNX model. And on Friday, we have AI for pros using deep learning for PyTorch. And it'll go into more depth about how can you use PyTorch and Azure ML to create your models. And when you have a PyTorch model, you can use kind of what I did to eventually export it or save it as an ONNX file. So you can operationalize it either in Windows ML or in Azure ML with the ONNX runtime. All right, so that's all the material I had. So thank you so much for joining, and have a good rest of your evening.